Please subscribe to support the channel. Astronomers are stunned. 3I Atlas has done something no comet has ever done before. Far beyond the warmth of the inner solar system, where sunlight is too weak to melt even the hardest ice, this interstellar traveler has begun releasing enormous amounts of water into space. It's venting vapor at a distance where every known comet should be silent and frozen, defying the very physics that govern comet activity. When telescopes first detected the unmistakable ultraviolet signature of water molecules breaking apart, scientists were floored. 3I Atlas isn't just another icy wanderer, it's a cosmic rule breaker, rewriting everything we thought we knew about how comets behave in the frigid reaches of space. The shock of 3I Atlas's unexpected water release was only the beginning. Once astronomers started measuring the scale of its outflow, astonishment turned into sheer disbelief. The numbers coming back from observatories didn't just challenge theories, they obliterated them. 3I Atlas isn't trickling out water in faint, occasional puffs like a dormant comet reluctantly stirring from its sleep. It's ejecting it in torrents, nearly 40 kilograms every single second. That's the equivalent of an entire bathtub's worth of water spewing into space every heartbeat, pouring from a frozen world more than 3 times the distance between Earth and the Sun. To put this into perspective, a typical comet at that distance would be as still and inert as a block of Antarctic ice in shadow. At over 3 astronomical units, or AUs, some light carries barely a tenth of the heat energy it delivers to Earth. The temperatures out there hover around -180 degrees Celsius or colder. At that range, even carbon dioxide, which sublimates more easily than water, begins to slow its escape. Yet somehow, 3I Atlas is thriving in that deep freeze, hurling out a staggering amount of vapor as if it were basking in the warmth of the inner solar system. Scientists double-check the data, assuming at first that it had to be an observational error. Maybe a background source had contaminated the readings, or perhaps an instrument calibration was off. But as the same measurements rolled in from different telescopes, NASA's Swift Observatory, the Hubble Space Telescope, and even the powerful James Webb Space Telescope, JWST, the truth became undeniable. Every instrument, every observation, every wavelength told the same story. The interstellar comet 3I Atlas was ejecting an impossible amount of water, consistently and dramatically. For astronomers, those numbers are mind-bending. 40 kilograms per second may not sound immense in everyday terms, but stretched across hours, days, and weeks, the scale becomes astronomical, literally. That's more than 3 million liters of water every day, enough to fill an Olympic swimming pool every couple of weeks. And this is all happening in a region of space where sunlight should be too weak to melt anything, where ices should remain locked in stasis until a comet ventures much closer to the Sun. This rate of ejection doesn't just break records, it breaks models. Theories of comet thermodynamics are built on how solar heating drives sublimation. The further a comet is from the Sun, the lower its activity should be, following a predictable exponential curve. But 3I Atlas sits far above that curve, outpacing expectations by a factor of hundreds. It behaves as though some hidden internal furnace is pumping heat through its icy body, yet there's no clear source for such energy. When astronomers calculated the total energy required for this much sublimation, the result was absurd. At that distance, sunlight alone could not possibly provide it. The comet's surface, even in direct sunlight, should remain far too cold for water ice to transition into gas. For 3I Atlas to lose that much water, something else must be happening, some unseen process stirring deep within its alien nucleus. But beyond the scientific equations, there's also a sense of awe. The very idea that an object traveling between stars could shed this much water in the empty dark carries poetic weight. It means that this tiny traveler, no larger than a mountain, is releasing part of its body into the cosmos, atom by atom, as it makes its brief passage through our solar system. Each molecule of water that drifts off its surface may have formed around another star billions of years ago, frozen in an alien nebula before our sun was even born. Now, that ancient water is evaporating into our skies, glowing faintly as ultraviolet light breaks it apart, a physical trace of another world mingling with ours. The sheer magnitude of the outflow suggests that 3I Atlas is far more active than a normal comet of its size should be. Even the most volatile rich comets in our solar system, like Comet Hale-Bopp, only reach that level of activity when they are within 1 AU of the Sun, about 150 million kilometers closer than where 3I Atlas is now. In other words, this interstellar visitor is performing like a comet in the inner solar system while standing out in the cold frontier where only sunlight's faint echo reaches.
This discovery has stunned planetary scientists and astrophysicists alike because it forces a reconsideration of what activity means for comets formed under alien conditions. If a body from another star system can vent this much water so far from any heat source, perhaps its chemistry or internal structure is fundamentally different. Maybe the ice inside 3I Atlas is mixed with exotic volatiles that store latent heat or react chemically to trigger sublimation. Or perhaps fractures within its crust have exposed fresh, super-volatile layers that rapidly evaporate once sunlight, even weak sunlight, touches them. No matter the explanation, the scale of what's happening is unprecedented. It's as though the comet's surface is alive with vents and geysers releasing frozen gases and water in a continuous, invisible storm. The plume of gas surrounding 3I Atlas, its coma, now stretches thousands of kilometers across, a vast, ghostly sphere reflecting sunlight in the darkness. That coma is so large and so active that astronomers can detect its composition directly from afar, using spectral lines that reveal the fingerprints of the molecules within it. And at the heart of all this activity is that astonishing figure, 40 kilograms of water every second. It's a number that captures just how alien this object truly is. For the first time, scientists are watching a comet that shouldn't exist in this state of activity, doing something no known comet has ever done, and doing it with such intensity that it forces an immediate reevaluation of how icy bodies behave in the galaxy. This isn't just a story of a comet, it's a story of extremes. 3I Atlas has taken the quiet expectation of cometary behavior and blown it wide open. The sheer power and persistence of its water release hint at a mechanism beyond our current understanding, a kind of hidden engine deep within the ice. For an interstellar visitor, perhaps formed under entirely different stellar chemistry, that engine might not obey the same rules we're used to. Whatever is driving this activity, one thing is clear. 3I Atlas is not just active, it's hyperactive. It is expelling more water at greater distances than any comet ever observed, challenging every assumption about the limits of solar influence. And that scale of discovery, that unthinkable torrent of ancient water, is what makes this moment in astronomy so electrifying. The true astonishment of 3I Atlas isn't just the sheer amount of water it's ejecting, but the environment in which this phenomenon is happening. At over 3 times the distance between Earth and the Sun, roughly 3 AU, water ice should be frozen solid, locked away in a state of permanent dormancy. In these frigid outer reaches, the Sun's energy is a mere whisper, far too weak to trigger the sublimation processes that typically drive cometary activity. By every known law of physics governing icy bodies in space, 3I Atlas should have been a silent, inert traveler, drifting along its interstellar trajectory with no visible sign of life. And yet, it is doing the exact opposite. To understand how unusual this is, consider how comets normally behave. Within our solar system, comets begin to show activity primarily when they venture close enough for solar radiation to warm their surfaces and sublimate their volatile ices. Water ice, being relatively stable, usually remains dormant until a comet is well inside the orbit of Mars, where sunlight becomes intense enough to warm the nucleus to temperatures above -100 degrees Celsius. Only then does the frozen water vaporize, forming the glowing comas and tails that have fascinated astronomers for centuries. Far beyond the zone, at distances like those of 3I Atlas, the temperature is generally too low for any significant water-driven activity. And yet, 3I Atlas is defying that expectation. Its surface is venting water at rates comparable to fully active comets much closer to the Sun. This defiance raises an immediate and profound question. What mechanism allows water ice to sublimate so efficiently in a place where sunlight is only a fraction as strong as at Earth? There are no simple answers. The comet may possess an unusual internal structure, where heat is trapped beneath insulating layers of dust and ice, gradually working its way to the surface. Or perhaps chemical reactions within the comet's interior, triggered by sunlight or interactions between trapped gases, are releasing energy sufficient to drive sublimation. The unusual nature of 3I Atlas's activity extends beyond just the distance factor. Most comets in our solar system display a low surface activity fraction. Typically, just a few % of their surface is actively venting gas and dust at any given time. Yet, for 3I Atlas to release water at the observed rates, estimates suggest that roughly a fifth of its surface must be actively venting. This scale of activity so far from the Sun is completely unprecedented. It is a clear signal that 3I Atlas is not merely a passive object in the solar wind, it is dynamically alive, reshaping our understanding of what is possible for icy bodies in the cold outskirts of planetary systems. The environment in which this occurs makes the phenomenon even striking. In these remote regions of space, temperatures typically hover around -180 degrees Celsius, a range in which water ice is almost completely inert. To see water being released at such a distance is like witnessing a candle burning in the middle of Antarctica. It shouldn't happen, and yet it does, demanding that astronomers rethink fundamental assumptions about the behavior of ice under extremely cold, low-energy conditions. Even among comets that originate within our solar system, such activity at 3 AU would be remarkable. Most of these comets only begin to display even minimal water sublimation when they approach within 2 AU or closer. And interstellar comets like 3I Atlas are even more mysterious because their formation and chemical composition may differ drastically from solar system comets. The combination of high water output, unusual distance, and rapid activity makes 3I Atlas not just rare, but almost singular in its behavior.
This unusual behavior also has implications for understanding the physical properties of 3I Atlas itself. The comet's ability to sublimate water so far from the Sun suggests that its ice may be mixed with other volatile compounds or arranged in a way that allows sunlight to penetrate and trigger activity at unexpected depths. Layers of dust may act as insulating blankets, trapping internal heat and creating pockets where sublimation can occur. Alternatively, highly porous ice structures may enable gas to escape from the interior more easily than in typical solar system comets, amplifying the observable water output. The phenomenon challenges our broader understanding of interstellar objects. 3I Atlas is only the third confirmed interstellar visitor ever detected, and unlike the dry Oumuamua or the more normal comet Borisov, its behavior is completely novel. The fact that water ice can sublimate efficiently at such extreme distances suggests that interstellar comets may operate under different physical and chemical rules than their solar system counterparts. Perhaps the conditions under which they formed, colder, more carbon-rich environments around other stars, create a structure and composition that allows for early and vigorous activity even under minimal solar heating. In essence, 3I Atlas is an anomaly that forces astronomers to question everything they thought they knew about cometary physics. It is not only defying expectations in terms of water output, but also in where that output is occurring. This unusual activity serves as a reminder that the universe is often far stranger than our models allow, and that interstellar visitors can bring entirely new behaviors that solar system comets simply do not display. In a way, 3I Atlas is whispering secrets about the diversity of icy worlds beyond our Sun. Its ability to vent water at such extreme distances reveals the potential for comets formed under alien conditions to behave in ways we have never anticipated, and to reshape our understanding of the limits of activity for frozen bodies in the cold void. Observing this behavior provides a rare window into the physics and chemistry of alien ices, potentially offering clues about how volatiles are stored, released, and transported across planetary systems. By simply existing and acting in ways that should be impossible, 3I Atlas is telling astronomers that their assumptions about distance, heat, and activity need serious revision. It is an unprecedented case study, a reminder that even far from the Sun, interstellar objects can behave in complex and surprising ways, releasing water where we would least expect it. The sheer unusualness of this phenomenon is a testament to how much we still have to learn about comets, interstellar chemistry, and the hidden dynamics of icy bodies drifting through the galaxy. The remarkable behavior of 3I Atlas might have remained mystery if not for the meticulous observations of astronomers across the globe. Detecting water from a comet that is so far from the Sun is no small feat. Water vapor itself is often invisible at vast distances, blending into the cold darkness of space. Instead, scientists rely on indirect but unmistakable signatures, the chemical fingerprints left behind when sunlight interacts with water molecules. And in the case of 3I Atlas, these signatures came in the form of ultraviolet light emitted by hydroxyl radicals, or OH fragments, a definitive clue that water was indeed being released. Hydroxyl radicals are produced when sunlight breaks water molecules apart through a process called photodissociation. Essentially, the energy from solar ultraviolet photons hits a water molecule, splitting it into hydrogen and hydroxyl. While the hydrogen quickly escapes into space, the hydroxyl radicals emit a characteristic ultraviolet glow as they relax to lower energy states. By observing this glow, astronomers can directly measure water production even when the comet itself is too faint or distant to reveal water vapor through other means. For 3I Atlas, this ultraviolet emission was a smoking gun, incontrovertible evidence that the comet was shedding water despite the frigid conditions so far from the sun. Detection was not trivial. Observatories had to point sensitive ultraviolet instruments at the comet and measure its light across very specific wavelengths. NASA's Swift Observatory, typically used to study gamma-ray bursts, played a crucial role here. Swift's ultraviolet imaging capabilities allowed scientists to capture faint emissions of OH radicals, tracing them as they expanded outward from the comet's nucleus. Each detection confirmed that water was being released at rates far beyond what should be possible at 3 AU. Other telescopes, including the Hubble Space Telescope, independently verified these observations, creating a robust dataset that left little room for doubt. What made this discovery even more impressive was the consistency of the measurements. Observatories around the world, observing in different ultraviolet bands, detected the same pattern, a steady production of hydroxyl radicals emanating from the coma of 3I Atlas. The brightness of these emissions directly correlates with the amount of water being released, and the numbers were staggering. It wasn't a minor trickle. It was a continuous, massive outflow, confirming that 3I Atlas was not only active, but hyperactive, producing water at rates equivalent to some of the most energetic comets in the inner solar system, all while lingering in a region of space so cold it should have been frozen solid. These ultraviolet measurements also allowed scientists to map the distribution of water around the comet. By observing how the hydroxyl radicals spread outward, astronomers could infer the geometry and structure of 3I Atlas's coma. They discovered that the water vapor wasn't just escaping from a few localized vents, but rather it appeared to be coming from a substantial portion of the surface, consistent with the earlier estimate that roughly a fifth of the comet's surface must be actively venting. This provided an important clue about the comet's internal structure, that it is far more porous or fractured than most comets we have studied, potentially containing layers of ice and gas that respond dynamically to even minimal solar heating. The detection of hydroxyl radicals also helped confirm the comet's interstellar nature. Unlike typical solar system comets, which often display predictable ratios of water to other volatiles, the chemical signatures in 3I Atlas hinted at a very different composition. Observing OH emissions allowed astronomers to calculate the water production rate in context with other measurements, such as carbon dioxide abundances observed by the James Webb Space Telescope. These combined datasets painted a picture of a comet that is both familiar and alien, shedding water like a normal comet, but in a way that is unprecedented for an object formed around another star. Ultraviolet detection of water is a method that has been employed for decades, from monitoring comets like Halley and Hale-Bopp to studying outgassing patterns in smaller solar system bodies. Yet even with all this experience, the signals from 3I Atlas were extraordinary. The brightness, consistency, and scale of the hydroxyl emission at such a distance were unlike anything astronomers had ever recorded. It confirmed not only the comet's water activity, but also its intensity, a level of activity comparable to comets in the inner solar system, far earlier and farther out than physics would have predicted. This is what made 3I Atlas's observation so compelling. The combination of ultraviolet evidence, corroborating data from multiple observatories, and the extreme distances involved created a story that couldn't be explained by conventional cometary models. Each hydroxyl radical detected in the comet's coma
represented water molecules that had traveled billions of kilometers from a distant star system before being split apart by our sun's faint ultraviolet light. In effect, scientists were witnessing interstellar water, ancient ice that had survived the journey across space, now breaking apart in our cosmic backyard. The meticulous detection process also highlighted the importance of modern observatories working in tandem. Swift, Hubble, and ground-based telescopes provided complementary data: ultraviolet emission, spectral analysis, and coma imaging. By cross-referencing these observations, astronomers could verify that the signal was indeed coming from water outgassing and not from other potential sources such as cosmic rays or stray starlight. The consistency across instruments strengthened the case that 3I Atlas is genuinely active in a way never seen before. Ultimately, the ultraviolet detection of hydroxyl radicals was more than a technical achievement. It was a revelation. It confirmed that 3I Atlas is a living, dynamic body, ejecting water in massive quantities at a distance where physics predicts it should be frozen solid. It provided concrete proof that this interstellar comet is defying expectations, opening a window into the processes that govern icy bodies formed around other stars. Each detection told astronomers a simple but profound truth: water is escaping from 3I Atlas, and it is doing so in a way that challenges everything we thought we knew about cometary activity. By noticing these hydroxyl emissions, scientists could not only quantify the water output, but also explore the deeper mysteries of this alien visitor: how its internal structure might store and release volatiles, what chemical compositions allow such distant activity, and what this implies for our understanding of interstellar comets as a whole. The detection of water via hydroxyl radicals was the key piece of the puzzle, proof that 3I Atlas is an extraordinary, unprecedented object, altering the very rules of cometary science. What makes 3I Atlas's water release truly extraordinary is the stark contrast between its behavior and what we observe in comets within our own solar system. For decades, astronomers have studied comets and learned a fairly consistent pattern. They become active only when they approach the sun closely enough for its heat to penetrate their frozen surfaces and warm their interiors. Water ice, being relatively stable, generally requires proximity to the sun, usually within 2 AU, to sublimate in noticeable quantities. Only at these distances do comets develop the glowing comas and tails that have fascinated humanity for millennia. Yet even with all this experience, 3I Atlas is behaving as though these rules no longer apply, venting massive amounts of water while lingering in the cold, dark outskirts of the solar system, far beyond where sunlight should be able to trigger any substantial activity. In typical comets, solar heating slowly warms the outer layers, creating pockets where sublimation begins. This process is gradual and localized, often affecting only a few % of the surface. As the comet approaches the sun, more volatile materials, such as carbon dioxide or methane, may begin to sublimate at slightly greater distances, producing minor activity. However, water, the most abundant and observationally important volatile, generally remains dormant until the comet is much closer. The fact that 3I Atlas is producing water so far out is therefore a profound deviation from this well-established pattern. Astronomers often compare comets' activity to a thermostat, controlled by solar heating. In this analogy, the sun is the only external energy source capable of turning on the heat inside a comet, causing frozen molecules to transition into gas. For 3I Atlas, however, this thermostat seems broken. It's venting water in a manner more typical of a comet deep within the inner solar system, despite existing at more than 3 times the Earth-Sun distance. The physical processes responsible for driving sublimation at this range must be different, or at least amplified by unknown mechanisms, making the comet's behavior unprecedented and scientifically astonishing. The extraordinary nature of this discovery lies not only in distance, but also in magnitude. 3I Atlas isn't producing a minor trickle of water. It is releasing about 40 kilograms per second, a rate comparable or exceeding many inner solar system comets at similar stages of their solar approach. This combination of high water output and remote location is what truly separates 3I Atlas from any comet previously studied. It forces astronomers to rethink the threshold at which water ice can become active and challenges long-standing models that rely exclusively on solar heating to explain cometary activity. Furthermore, this behavior raises immediate questions about the comet's internal structure and composition. If sunlight alone cannot account for the observed water release, there must be mechanisms within 3I Atlas enabling this activity. Scientists speculate that trapped gases, crust fractures, or chemical reactions inside the ice may provide the energy needed to drive sublimation. Perhaps 3I Atlas contains highly volatile compounds beneath an insulating crust, which, when exposed, can catalyze water release even under minimal solar illumination. Whatever the explanation, it demonstrates that comets formed around other stars can behave in ways entirely foreign to the solar system norms. The extraordinary activity of 3I Atlas also highlights the comet's interstellar significance. Unlike solar system comets, which follow predictable patterns of activity as they travel through known thermal environments, 3I Atlas carries a record of conditions from a distant star system. Its unexpected water sublimation at extreme distances provides an unprecedented glimpse into the physical and chemical properties of icy bodies beyond our own sun. Observing it not only challenges existing cometary science, but also expands our understanding of how volatile materials behave in alien planetary systems. In practical terms, this behavior is rewriting textbooks. The assumption that water-driven activity begins only when comets are exposed to strong solar radiation no longer universally applies. 3I Atlas proves that interstellar comets may operate under different rules, shaped by formation environments far colder and richer in carbon than the region in which solar system comets were born. For astronomers, this is an extraordinary revelation, offering a rare opportunity to study the mechanisms driving water sublimation outside the conventional solar paradigm. Ultimately, the extraordinary nature of 3I Atlas lies in its combination of distance, intensity, and interstellar origin. It is a water-producing comet far beyond the solar safe zone, doing what no other comet has been observed doing and revealing processes that challenge our deepest assumptions about cometary science. By simply existing and behaving in this way, 3I Atlas is teaching astronomers that the universe is far more inventive than previously imagined, and that even in the deep freeze of space, water can find a path to liberation. To fully appreciate the extraordinary nature of 3I Atlas, it's important to place its activity in the context of what we typically observe in comets. Most comets, even when they are relatively close to the Sun, have only a small fraction of their surface actively venting gas and dust. Observations of well-studied solar system comets, such as Halley, Hale-Bopp, or 67P Churyumov-Gerasimenko, show that typically just a few percent of their surfaces are actively sublimating. This limited activity is largely due to the insulating effect of dust layers, the uneven distribution of volatiles, and the gradual penetration of solar heat into the comet's interior. Even within these small active regions, the outgassing can create spectacular comas and tails, but the bulk of the nucleus remains relatively dormant. Now consider 3I Atlas. For this interstellar visitor to release about 40 kilograms of water per second, the active fraction of its surface must be far larger than what is typical for solar system comets. Calculations suggest that roughly a fifth of its surface is actively venting gas and ice at any given time. This is an enormous proportion when compared to comets that have been extensively studied closer to the Sun. It indicates a level of global activity that is almost unheard of, especially at such a great distance from solar radiation, where most comets would be completely inert. This high active fraction has multiple implications. First, it suggests that the surface of 3I Atlas may be unusually fractured, porous, or otherwise exposed, allowing subsurface ice and trapped volatiles to escape efficiently.
Whereas most comets develop localized vents in areas where sunlight penetrates thin dust layers, 3I Atlas appears to have extensive regions of sublimation. This widespread activity might reflect its interstellar origins, pointing to formation conditions in a cold, volatile, rich environment that allowed for a relatively uniform distribution of ices near its surface. Moreover, the need for such a large fraction of active surface to explain the observed water production challenges previous assumptions about cometary behavior. In solar system comets, it's rare for more than 10 to 15% of the surface to be significantly active at any given moment, even when the comet is in the inner solar system. That 3I Atlas exhibits twice or more this level of activity so far from the sun underscores just how unusual it is. It's not merely active in isolated patches. It's engaging in sustained high-level sublimation over a substantial portion of its nucleus. The scale of surface activity also helps explain the size of the comet's coma. When such a large fraction of the nucleus is venting material, the expelled gas and dust spread outward, forming a vast, glowing envelope around the comet. Observations of 3I Atlas confirm a coma that is not only extensive, but also dense enough for astronomers to detect water through ultraviolet emissions and carbon dioxide through infrared measurements. In other words, the comet's activity isn't just localized, it's a global phenomenon, producing a measurable atmosphere-like cloud in the cold vacuum of interstellar space. This context also raises fascinating questions about the comet's internal structure and thermal properties. If nearly 1/5 of the surface is actively venting, then the subsurface layers must be unusually rich in volatiles and capable of responding to minimal sunlight at extreme distances. The distribution of active regions might indicate that the nucleus has thin crusts or fractures exposing ice layers, or that trapped gases within the comet are being released as internal pressures build and find escape paths. Unlike typical comets where only certain patches near the surface are responsive to solar heating, 3I Atlas seems to have much larger expanses of volatile rich material available for sublimation. In addition, this high level of activity challenges previous models of interstellar comet behavior. Oumuamua, the first confirmed interstellar object, showed no visible signs of outgassing, while Borisov, the second, behaved largely like a typical solar system comet, with a modestly active surface. 3I Atlas, by contrast, is exceptionally active over a significant portion of its surface, releasing water at rates far higher than would be expected for its distance and size. This makes it a unique opportunity to study how interstellar comets can differ dramatically from solar system counterparts, offering insights into the diversity of formation conditions in alien planetary systems. Finally, understanding the context of activity is essential for interpreting other observations, such as the comet's brightness, gas output, and the relative abundances of water and carbon dioxide in its coma. The fact that nearly 20% of the surface is venting explains why the comet is so luminous in ultraviolet and infrared wavelengths, and why its activity can be sustained over such vast distances. Without this high fraction of active surface, the water production rates observed would simply be impossible, reinforcing just how extraordinary 3I Atlas is as a physical object. While 3I Atlas's extraordinary water output already challenges our understanding of cometary physics, the picture becomes even more fascinating when we examine its composition. Data from the James Webb Space Telescope, WAJST, revealed a surprising detail. Despite all the attention on its water vapor, the coma of 3I Atlas is overwhelmingly dominated by carbon dioxide, not water. The measurements indicate a ratio of approximately 8 parts CO2 to 1 part water, a chemical balance that is highly unusual when compared to comets formed in our solar system. This discovery adds another layer of intrigue to an already extraordinary object and points to a very alien formation environment. In solar system comets, water typically dominates the volatile content. Even for comets rich in carbon-based compounds, water often takes up the majority of sublimating material when the comet approaches the sun. Carbon dioxide, while present, usually exists in smaller quantities relative to water. In contrast, 3I Atlas exhibits a CO2-dominated coma, meaning that the majority of the gases escaping its nucleus are carbon dioxide molecules, with water playing a secondary role. This inversion of expected ratios is striking and immediately signals that 3I Atlas is chemically distinct from the comets we know best. The WHAST data were particularly revelatory because of the telescope's unparalleled sensitivity in the infrared spectrum. Carbon dioxide absorbs and emits strongly in infrared wavelengths, allowing astronomers to precisely measure its abundance in the coma. By combining these observations with ultraviolet measurements of water via hydroxyl radicals, researchers were able to determine not only that water was being released, but that it is far less abundant than carbon dioxide in the surrounding gas envelope. In other words, while 3I Atlas is ejecting enormous amounts of water, it is releasing even more CO2, painting a picture of a comet whose chemistry is far from ordinary. This CO2 dominance also has implications for understanding the physical mechanisms driving activity at such extreme distances. Carbon dioxide is far more volatile than water ice, sublimating at much lower temperatures. Its prevalence in the coma suggests that CO2 may play a critical role in powering the outgassing of the comet, even far from the sun. It is plausible that sublimation of carbon dioxide is responsible for initiating or sustaining the release of water, effectively acting as a catalyst for the activity we observe. In this sense, CO2 could be a key piece of the puzzle explaining how 3I Atlas is active in conditions that would normally be too cold for water to sublimate on its own. Moreover, the CO2-to-water ratio provides insight into the comet's interstellar origins. The high abundance of CO2 suggests that 3I Atlas likely formed in a colder, more carbon-rich environment than comets in our solar system. In such regions, volatile carbon compounds condense more readily than water ice, leading to a composition skewed toward carbon dioxide and other frozen gases. This aligns with models of planetesimal formation in the outer regions of protoplanetary disks around other stars, where temperatures are extremely low and carbon compounds dominate the chemistry. In essence, the CO2-rich coma is a chemical fingerprint, revealing that 3I Atlas is a product of a very different stellar nursery than the one that produced our own solar system. The CO2 dominance also has practical observational consequences. Carbon dioxide sublimation contributes significantly to the comet's brightness in infrared observations, enhancing the visibility of 3I Atlas's coma even at great distances from the sun. It explains why instruments like James Webb Space Telescope and ground-based infrared telescopes can detect the comet so clearly, despite its remote location. Additionally, the high CO2 abundance helps astronomers estimate the internal composition and thermal structure of the comet, suggesting that large reservoirs of volatile carbon are present beneath the surface, ready to be released when the comet receives even minimal sunlight.
In comparison to other interstellar visitors, 3I Atlas is unique in this chemical sense as well. Oumuamua, the first interstellar object, showed no detectable coma and was apparently dry, leaving astronomers puzzled about its composition. Borisov, the second interstellar comet, displayed water and carbon-bearing molecules in ratios somewhat similar to solar system comets. 3I Atlas, however, behaves in a way that is both physically and chemically distinct. Not only is it ejecting water at unprecedented distances, but it is doing so while its coma is chemically dominated by carbon dioxide, a striking reversal of the patterns we see in known comets. This CO2 dominance provides a critical clue to understanding 3I Atlas's extreme behavior. The presence of highly volatile carbon dioxide likely facilitates sublimation in regions where sunlight is too weak to directly vaporize water ice. The CO2 may even generate internal pressures that fracture the surface, exposing water-rich layers and driving the observed water outflow. In this way, the unusual chemistry is not just a curiosity. It may be the key to solving the mystery of why this comet is so hyperactive at such a frigid distance. In summary, the JWST observations revealing a CO2-to-water ratio of roughly 8:1 confirm that 3I Atlas is chemically alien compared to solar system comets. Its outgassing is dominated by carbon dioxide, and water plays a supporting but still significant role. This unexpected chemical profile provides a window into the comet's interstellar origins, suggesting formation in an extremely cold, carbon-rich environment, and hints at the mechanisms driving its activity in regions of space where most comets would be dormant. The CO₂ connection underscores the uniqueness of 3I Atlas, making it not only physically exceptional, but chemically unlike any comet previously studied. The striking imbalance between carbon dioxide and water in 3I Atlas's coma, roughly 8 parts CO₂ to 1 part water, is far more than a chemical curiosity. It provides a tantalizing clue about the comet's birthplace and formative environment. In our solar system, comets tend to have water as the dominant volatile, with carbon dioxide, carbon monoxide, and other gases present in smaller proportions. This is because our protoplanetary disk had a relatively moderate temperature gradient, with water ice condensing efficiently in the outer regions, while carbon-rich ices were less abundant. For 3I Atlas, the reverse pattern suggests that it did not form in such a disk. Instead, its composition points to a much colder, more carbon-rich region around another star, where temperatures were low enough to favor the condensation of carbon dioxide and other highly volatile compounds over water. This inference is consistent with models of planet formation in distant, icy regions of protoplanetary disks. In the outermost zones of such disks, sometimes tens or hundreds of astronomical units from the host star, temperatures can plunge to just a few tens of Kelvin. In these environments, carbon-bearing molecules such as CO₂, CO, and methane condense readily, while water may remain trapped in deeper layers or be less abundant relative to carbon compounds. The high CO₂-to-water ratio in 3I Atlas strongly suggests that it originated in one of these ultra-cold carbon-rich zones, making it chemically distinct from the comets we are familiar with in our own solar system. Furthermore, this chemical signature carries implications for the history and evolution of 3I Atlas. The comet's composition implies that it has retained a significant portion of its original volatile inventory over billions of years and light years of travel. Unlike solar system comets, which often lose surface volatiles during repeated perihelion passages around the Sun, 3I Atlas has been largely insulated from stellar radiation until its recent approach to the solar system. This preservation of its primordial ices allows us to peek into the conditions of a planetary system far beyond our own, providing a rare glimpse of the building blocks from which other stars' comets and potentially planetary bodies formed. The high carbon dioxide content also offers clues about the physical processes occurring within the comet. CO₂ sublimates at much lower temperatures than water ice, making it a more efficient driver of activity at great distances from the Sun. This may help explain why 3I Atlas is so active in a region where water ice alone would normally remain frozen. The sublimation of CO₂ could generate enough internal pressure to fracture the surface layers, exposing water ice and allowing it to sublimate despite the cold environment. In other words, the chemical imbalance is likely a key factor enabling the comet's unusual activity. This interpretation aligns with what astronomers have learned from observing other interstellar objects and extreme solar system comets. While solar system comets occasionally show elevated CO₂ abundances, a ratio as high as 8:1 is exceptional and has no direct analog in our own planetary neighborhood. It strongly supports the idea that 3I Atlas formed in an alien environment with conditions markedly different from the protoplanetary disk of our own Sun, one that was both colder and richer in carbon-based volatiles. From a broader perspective, this chemical imbalance also provides insight into the diversity of planetary systems across the galaxy. The fact that 3I Atlas has such a high CO₂-to-water ratio suggests that the composition of icy bodies can vary dramatically depending on where they form. It opens the door to the possibility that many other interstellar comets may carry similarly unusual chemical signatures, offering a window into the variety of planetary formation environments that exist beyond our solar system. Observing and interpreting these imbalances is a key step towards understanding the full spectrum of planetary chemistry across the Milky Way. Moreover, the CO₂-dominant coma hints at the thermal and structural history of 3I Atlas. The comet's interior likely retained large reservoirs of highly volatile materials, which have remained trapped until exposure to sunlight in the outer solar system. This contrasts with typical comets closer to the Sun, where surface volatiles have often been depleted after repeated perihelion passages. The unusual composition of 3I Atlas thus reflects both its birthplace and its remarkable preservation over its interstellar journey. In summary, the extreme CO₂-to-water imbalance observed in 3I Atlas is a powerful diagnostic tool. It strongly suggests that this comet formed in a colder and carbon-rich region around another star, far beyond the conditions found in our own solar system. This origin story helps explain both its unusual chemistry and its remarkable activity at great distances from the Sun. By studying this imbalance, astronomers are not only learning about the comet itself, but also gaining a rare glimpse into the chemical diversity of other planetary systems, providing a broader context for understanding the origins of water, carbon, and potentially the ingredients for life throughout the galaxy. The chemical makeup of 3I Atlas is not just unusual, it's fundamentally different from anything we typically observe in our solar system. In comets formed around our Sun, water ice overwhelmingly dominates the volatile content, with carbon dioxide, carbon monoxide, and other gases usually present only in minor amounts. Even the most extreme comets within the solar system rarely exhibit CO₂ ratios approaching what has been observed in 3I Atlas. A ratio of roughly 8:1 is exceptional. In fact, it has no true analog among solar system comets. This stark difference underscores that 3I Atlas is not just another icy visitor, it's a chemical outlier, providing a direct window into the diversity of planetary system formation across the galaxy. For astronomers, this is profoundly illuminating. 3I Atlas demonstrates that icy bodies forming around other stars can have compositions radically distinct from what we consider normal. While solar system comets offer insights into the materials and conditions present in our own stellar nursery, 3I Atlas offers a glimpse of entirely alien chemistry, a world where carbon dioxide dominates, where water, though present, plays a secondary role, and where volatiles may be arranged in ways we have never seen before. Studying such an object allows scientists to expand their understanding of planetary formation beyond the confines of the Sun's protoplanetary disk, opening a window into the variety of conditions that may exist around other stars. This chemical distinctiveness also has broader implications for our understanding of cometary activity. In solar system comets, activity is usually governed by water sublimation as the primary driver, with CO₂ and other volatiles playing supporting roles. In 3I Atlas, however, the comet's unusual CO₂ dominance suggests that activity may be largely fueled by these highly volatile compounds, enabling water ice to sublimate even at distances where sunlight is insufficient to drive water activity on its own. In other words, 3I Atlas is demonstrating a mode of cometary behavior that we have never witnessed within our own system, offering new insights into how interstellar comets might operate. Observing 3I Atlas is also a reminder that our models of cometary chemistry are inherently biased by the solar system examples we have studied. Until now, our understanding of how comets form, evolve, and become active has been strongly shaped by a handful of well-characterized comets orbiting our Sun.
Interstellar comets like 3I Atlas challenge these assumptions, showing that the rules we take for granted about volatile composition, activity thresholds, and chemical dominance may not apply universally. It's a humbling realization. The universe is far more diverse than the few comets we have sampled locally might suggest. Beyond chemistry, 3I Atlas's differences extend to its physical behavior. The high fraction of its surface that is actively venting water and CO2 at extreme distances, coupled with its unusual chemical composition, makes it unlike any comet previously studied. While some solar system comets can appear hyperactive when near the sun, none combine early activity, CO2 dominance, and such large-scale venting simultaneously. This combination of traits gives astronomers an unprecedented opportunity to study processes that may be common in other stellar systems but are rare or absent in our own. Ultimately, 3I Atlas provides a glimpse of the potential diversity of icy bodies throughout the galaxy. By comparing its properties to solar system comets, scientists can begin to understand what might be typical or atypical in different planetary systems. Its CO2-rich composition, high surface activity, and ability to release water so far from the sun suggest that icy bodies from other stars may behave very differently from what we have come to expect. In essence, 3I Atlas is teaching us that planetary system formation can produce a far wider variety of chemical and physical structures than previously imagined, offering a tantalizing preview of the kinds of interstellar comets that may be discovered in the future. In short, 3I Atlas is not merely unusual, it is alien in the truest sense. Its chemistry, activity, and interstellar origin together highlight the diversity of conditions under which icy bodies can form. By studying it, astronomers gain a rare window into how comets from other planetary systems might be composed, how their activity may differ from solar system norms, and what this tells us about the chemical richness of the galaxy. 3I Atlas is more than a comet. It is a messenger from another stellar nursery, revealing the extraordinary possibilities for the formation and evolution of icy worlds beyond our sun. The more astronomers study 3I Atlas, the more enigmatic it becomes. Its extreme activity at such a great distance from the sun raises a fundamental and perplexing question. If sunlight is too weak to melt the ice, what is driving this dramatic outburst of water and carbon dioxide? According to conventional cometary physics, the sun's energy at over 3 astronomical units should be insufficient to trigger significant sublimation of water ice. And yet, 3I Atlas is venting gas at a rate and scale comparable to comets much closer to the sun, producing a vast active coma. This paradox lies at the heart of the mystery surrounding this interstellar visitor. Scientists have proposed several possible explanations, none of which are fully confirmed, but all of which highlight the complexity and novelty of 3I Atlas. One leading idea involves trapped gases within the comet's interior. Over its long interstellar journey, 3I Atlas may have accumulated pockets of volatile gases beneath an insulating crust. When exposed to even minimal sunlight, these gases could expand, creating pressure that fractures the surface and forces both CO2 and water vapor to escape. In this scenario, sunlight acts not as a direct heat source for water sublimation, but as a trigger that allows the stored internal energy to be released in spectacular outbursts. Another possibility focuses on surface fractures or cracks in the comet's crust. Comets are often irregular, porous, and riddled with fissures formed during their formation or through stress over billions of years. On 3I Atlas, even weak solar heating could cause small expansions or contractions, opening these fractures and exposing volatile-rich layers underneath. Once these pockets are revealed, both carbon dioxide and water could sublimate more easily, producing the continuous water outflow observed by telescopes. This mechanism could explain why roughly a fifth of the comet's surface appears active, an unusually high fraction, far more than seen in typical solar system comets at comparable distances. A third intriguing hypothesis involves chemical reactions within the dust and ice mixture itself. Some types of reactions in cometary ices can release energy, potentially providing localized heat that triggers sublimation. For example, certain hydrated minerals or clathrates, ice structures that trap gas molecules, may break down when exposed to small amounts of energy, releasing both gas and heat in the process. If 3I Atlas contains exotic ices formed in a carbon-rich, ultra-cold interstellar environment, such reactions could occur more readily than in solar system comets, providing an additional mechanism to drive water outflow at vast distances from the Sun. Each of these possibilities underscores how little we know about the detailed physics of interstellar comets. Solar system comets serve as our primary models, but 3I Atlas is demonstrating that interstellar objects can behave in ways that defy these models. Its early and intense activity may result from a combination of mechanisms: the sublimation of CO2 acting as a primary driver, fractures in the nucleus allowing water to escape, and potentially chemical reactions releasing additional heat from within. The interplay of these processes could explain how water is being released far earlier and farther from the Sun than any known comet in the solar system. The mystery also highlights the challenges astronomers face in studying interstellar objects. Unlike solar system comets, which can be monitored repeatedly over long orbital periods, 3I Atlas is a transient visitor, traveling at high speed on a trajectory that will soon take it far from observational reach. Understanding its activity in real time requires coordinated observations across multiple telescopes and wavelengths, from ultraviolet detection of hydroxyl radicals to infrared mapping of carbon dioxide. Every piece of data helps scientists narrow down potential explanations for this outburst, but no single theory yet accounts fully for the combination of early activity, high water output, and CO2 dominance. This mystery also raises profound questions about what we might expect from other interstellar comets. If 3I Atlas is capable of releasing water and carbon dioxide in this unusual way, then icy bodies formed in alien planetary systems may exhibit a much wider variety of behaviors than we've imagined. Some may remain dormant like Oumuamua, while others, like Borisov, resemble familiar solar system comets at comparable distances. 3I Atlas represents a third category entirely, chemically and physically alien, yet dynamically active in ways that stretch our understanding of cometary physics. Ultimately, the driving force behind 3I Atlas's outburst remains one of the great cosmic mysteries of the moment. Is it trapped gases building pressure, fractures exposing volatile-rich layers, chemical reactions within the ice, or some combination of all three? And could there be mechanisms entirely unknown to us, unique to interstellar objects formed in distant star systems? Each observation brings us closer to understanding, yet simultaneously deepens the intrigue. In this sense, 3I Atlas is not just a comet. It is a puzzle in motion, a real-time experiment of interstellar ice chemistry, and a challenge to centuries of assumptions about how icy bodies behave. Its outburst is a vivid reminder that the universe is inventive, and that phenomena we consider impossible within the solar system can in fact occur in alien environments. The question of what drives 3I Atlas will likely occupy astronomers for years, inspiring new models of cometary activity and theories about the composition and dynamics of interstellar icy bodies. One of the most remarkable aspects of 3I Atlas's behavior is the timing of its water activity. Observations indicate that the comet began venting water while still far from the Sun, long before any typical heating-driven sublimation could occur. In most solar system comets, water ice remains dormant until the object approaches roughly 2 AU or closer, when solar radiation becomes strong enough to penetrate the surface and warm the nucleus. At that point, the familiar glow of the coma and tail begins to develop, signaling the transition from dormancy to active outgassing. 3I Atlas has broken this rule entirely, initiating massive water release while still in the cold reaches beyond 3AU. This early onset of activity is unprecedented. In effect, the comet behaves as if the usual thermal threshold for water sublimation doesn't apply. Observatories detected the signatures of hydroxyl radicals, the UV fingerprints of water molecules being split by sunlight, well before the sun could have directly warmed the nucleus sufficiently to drive such behavior. The outflow was not a delayed reaction or an anomalous spike near perihelion. It started consistently at extreme distances, signaling that some mechanism other than conventional solar heating is enabling this activity. The timing emphasizes how just alien 3I Atlas truly is. For solar system comets, distance from the sun serves as a reliable predictor of activity. The farther away, the colder the ice, and the less likely sublimation is to occur. 3I Atlas defies this pattern entirely. Its water activity began weeks, even months earlier than we would expect for a comet at that location, showing that either its ice is extraordinarily sensitive to minimal sunlight, or that alternate internal processes are powering the outgassing.
This early activity also amplifies the implications for the comet's internal composition and structure. If water is escaping before conventional heating is possible, it suggests the presence of highly volatile materials beneath the surface, internal pressure built up over time, or chemical reactions within the ice that release energy independently of sunlight. The timing indicates that the comet's interior is not just cold and inert, but dynamically primed to release volatiles at the first hint of energy, even when that energy comes from weak solar illumination far from the sun. In addition, the early onset challenges how astronomers interpret cometary brightness and gas production. Many models rely on the assumption that a comet activity correlates strongly with its proximity to the sun. With 3I Atlas, these models fail to explain the observed water production at a distance where traditional sublimation should be negligible. This makes 3I Atlas a natural laboratory for testing alternative mechanisms of outgassing, from trapped gas reservoirs to fractures in the crust to exotic chemical reactions within the ice. Its timing forces scientists to reconsider the temporal dynamics of cometary activity, particularly for objects formed in alien planetary systems. Moreover, the timing has observational significance. The early activity allowed astronomers to detect and measure water and carbon dioxide emissions long before the comet reached perihelion, giving them a longer baseline to study its behavior, and helping to distinguish intrinsic properties from temporary or distance-dependent phenomena. The fact that the activity began at such a remote location strengthens the evidence that 3I Atlas is genuinely unusual, not just a comet experiencing a brief outburst due to chance heating events. Ultimately, the timing of 3I Atlas's water release is a central part of its mystery and scientific value. By starting far from the sun and well before typical sublimation thresholds, it demonstrates that interstellar comets can behave in fundamentally different ways from the solar system bodies we studied. Its early activity is a clue, a puzzle piece, and a direct challenge to our understanding of comet physics, a vivid signal that the rules governing icy bodies may be far more diverse when we look beyond our own star system. The extraordinary activity of 3I Atlas would have remained speculative if not for the coordinated observational efforts carried out by astronomers using multiple world-class observatories. To verify such unusual water release far from the sun required a combination of ultraviolet, optical, and infrared measurements, and the results from these independent observations converged on the same conclusion. 3I Atlas is genuinely venting water and other volatiles at a scale and distance previously unseen in any comet. This collaborative approach left little room for doubt and cemented the object's status as an unprecedented interstellar visitor. The Swift Observatory, primarily known for its role in monitoring gamma-ray bursts, played a critical role in detecting ultraviolet emissions from hydroxyl radicals. These radicals, produced when water molecules are split by sunlight, act as direct tracers of water vapor in the coma of the comet. Swiss sensitive ultraviolet imaging captured the spatial distribution and intensity of these radicals, providing the first confirmation that water was actively being released. The telescope's repeated measurements over time revealed a steady outflow, indicating that the activity was sustained rather than a transient or localized event. In parallel, the Hubble Space Telescope contributed high-resolution imaging and spectroscopy in ultraviolet and optical wavelengths. Hubble's data allowed astronomers to map the structure of 3I Atlas's coma in exquisite detail, revealing the extent and geometry of the water outflow. By comparing the emission patterns with models of cometary activity, scientists could estimate the fraction of the comet's surface contributing to outgassing, and confirmed that roughly a fifth of the nucleus was actively venting. This observation was critical as it linked the unusual magnitude of water release to a substantial portion of the comet's surface, rather than to a few isolated jets. Perhaps most strikingly, the James Webb Space Telescope provided complementary infrared observations which were key to assessing the chemical composition of the coma. JWST detected strong signatures of carbon dioxide and confirmed that the CO₂-to-water ratio in the coma was around 8:1. These infrared measurements validated the idea that 3I Atlas is chemically alien compared to solar system comets, and helped explain how water sublimation could occur so far from the sun. The sublimation of CO₂ at low temperatures could drive the release of water. The synergy between ultraviolet and infrared observations gave astronomers a multidimensional picture of the comet activity and composition. Ground-based observatories also played a crucial role in corroborating the findings. Telescopes equipped with sensitive spectrometers observed the comet in visible and near-infrared wavelengths, detecting emissions from both water and other volatiles. These measurements confirmed that the activity was not a localized anomaly in the field of view of a single space telescope. Rather, it was a genuine global phenomenon. Observatories on different continents, observing under different conditions and using different instruments, all reported consistent results, reinforcing the robustness of the conclusions. The scale of this observational effort cannot be overstated. Tracking an interstellar comet moving at high velocity through the solar system requires careful coordination, precise timing, and rapid data analysis. Observatories had to adjust their schedules and allocate precious observing time to capture the comet as it passed through the outer reaches of the solar system. The result of this global effort was an unprecedented dataset, spanning ultraviolet, visible, and infrared wavelengths, providing a comprehensive view of both the quantity and composition of the outgassed material. Importantly, the consistency across multiple observatories also rules out alternative explanations for the observed signals. For instance, faint ultraviolet emissions could theoretically arise from background stars or cosmic rays. But the correlated detection of hydroxyl radicals from SWIFT, combined with Hubble's imaging and JWST's infrared spectral data, leaves little doubt that the source is genuine water vapor being released from 3I Atlas itself. This cross-confirmation is a critical part of establishing scientific certainty for such a unique object. The observational effort also highlighted the power of modern astronomical collaboration. Interdisciplinary teams of astronomers, chemists, and planetary scientists analyzed data from a range of instruments to build a coherent narrative of 3I Atlas's activity. Each telescope contributed a piece of the puzzle. SWIFT revealed the water, Hubble showed its distribution, JWST uncovered the chemical composition, and ground-based observatories confirmed the findings from independent vantage points. Together, these observations provide compelling proof that 3I Atlas is not only venting water and CO₂ at an extraordinary rate, but is doing so in a way that is consistent, repeatable, and measurable. Ultimately, this coordinated observational effort is what allows scientists to study 3I Atlas with confidence. Far from relying on a single measurement or isolated event, astronomers can trace its activity across multiple wavelengths, timeframes, and instruments.
This comprehensive approach solidifies the comet's status as an unprecedented interstellar visitor and ensures that its extreme water and CO2 outgassing are genuine, measurable phenomena, not artifacts or observational errors. It is through this global, multi-instrument scrutiny that the remarkable nature of 3I Atlas has been revealed, giving researchers a unique window into an alien world that challenges our understanding of cometary physics, interstellar chemistry, and the diversity of icy bodies across the galaxy. The interstellar origin of 3I Atlas adds a profound dimension to its significance. Unlike comets formed within our solar system, which reflect the conditions and chemistry of the Sun's protoplanetary disk, 3I Atlas originated around another star, traveling across light years before its brief encounter with our planetary neighborhood. Its composition, dominated by carbon dioxide, yet releasing remarkable amounts of water, provides a rare and invaluable glimpse into the nature of icy bodies from alien star systems. In other words, the very fact that we can observe water and CO2 sublimation in 3I Atlas confirms that these volatile ices exist elsewhere in the galaxy beyond the confines of our own solar environment. This realization is both humbling and exciting. For decades, scientists have speculated about the universality of water and other volatiles across planetary systems, but direct evidence has been scarce. 3I Atlas provides that evidence in a strikingly tangible form. Its CO2-rich coma demonstrates that carbon-based volatiles can be abundant in protoplanetary environments far colder and more carbon-rich than our own solar system. At the same time, its ability to release water, even at extreme distances from the Sun, confirms that water ice, a crucial ingredient for life as we know it, can form and survive in interstellar space, carried across the galaxy within cometary bodies. The comet's interstellar journey also emphasizes the resilience and longevity of these ices. For 3I Atlas to reach the solar system with substantial amounts of CO2 and water still intact, its volatile inventory must have been preserved over millions or even billions of years and across vast distances through the interstellar medium. This suggests that icy bodies from other star systems can remain chemically pristine despite long-term exposure to cosmic radiation and the extreme cold of space, preserving the chemical signatures of their birth environment. The comet is, in effect, a frozen time capsule, carrying the history of a distant planetary system into our observational reach. The implications extend beyond chemistry, into the broader question of planetary system formation. Observing water and carbon dioxide in 3I Atlas confirms that the processes that create icy bodies, condensation of volatiles, trapping of gases, and incorporation of these ices into small bodies, are not unique to our Sun. The presence of these ices in an interstellar comet indicates that the building blocks for comet-like bodies are widespread across the galaxy, potentially forming in a variety of stellar environments. Each interstellar comet we encounter may carry distinct compositions reflecting the diversity of conditions under which planetary systems form. Moreover, 3I Atlas's interstellar origin provides context for its unusual behavior. Its chemical imbalance, high CO2-to-water ratio, and large fraction of active surface all point to formation in a protoplanetary disk far colder and more carbon-rich than our own solar system. By studying its activity and composition, astronomers can infer the conditions of an alien planetary system, the temperature gradient, chemical abundances, and possible distribution of volatiles. In this way, 3I Atlas serves as a messenger from another star, telling a story about the diversity of planetary formation across the Milky Way. The comet's interstellar journey also reminds us of the cosmic connections between distant star systems. The fact that water ice can survive long interstellar voyages and then become active when exposed to a new star's radiation illustrates the universality of volatile chemistry in the galaxy. Water and carbon-based ices are not confined to our local neighborhood. They exist in other stellar nurseries and can be transported across interstellar space, potentially seeding planetary systems far from their point of origin. This has profound implications for understanding the distribution of the ingredients for life throughout the galaxy. 3I Atlas also contrasts with its interstellar predecessors, emphasizing its unique contribution to our understanding of galactic chemistry. Oumuamua showed no signs of volatiles, leaving its composition a mystery, while Borisovov resembled a typical solar system comet with water-dominated activity. However, 3I Atlas is chemically distinct and dynamically active, demonstrating that interstellar comets can carry significant ices of both water and carbon dioxide preserved from their birth environments. This confirms that other star systems can produce a wide variety of icy bodies, each with potentially unique chemical fingerprints. In short, 3I Atlas's interstellar origin makes it much more than a passing comet. It is a chemical ambassador from another star, carrying frozen water and carbon dioxide across the galaxy and revealing that these crucial ices are not unique to our solar system. Its composition proves that the ingredients for cometary activity, and potentially even the raw materials for life, exist elsewhere in the galaxy, waiting to be discovered by our telescopes. By studying 3I Atlas, astronomers are gaining a window into the chemical richness of other planetary systems, helping us understand not only how comets form, but also how widespread the key building blocks of planets and life may be throughout the Milky Way. The presence of both water and carbon dioxide in 3I Atlas has implications that extend far beyond cometary science. It touches on one of humanity's most profound questions: how common are the ingredients for life in the galaxy? By demonstrating that water ice exists in an interstellar comet originating from another star system, 3I Atlas provides strong evidence that the basic chemical building blocks necessary for life are not unique to the solar system. If a comet formed around a distant star can carry preserved water and carbon compounds across light years, it suggests that similar icy bodies, and by extension the molecules essential for life, may be widespread throughout the galaxy. This strengthens a growing body of evidence that water, carbon, and other volatiles are likely abundant in planetary systems far beyond our own. Water is fundamental not only for life as we know it, but also for chemical processes that produce complex organic molecules. The fact that 3I Atlas carries water alongside CO2 suggests that these volatiles can coexist and survive over billions of years and across vast interstellar distances. This indicates that other star systems are likely capable of forming icy bodies rich in water and organics, potentially delivering these materials to planets or moons in those systems, just as comets in our own solar system may have contributed to Earth's oceans and prebiotic chemistry. Moreover, 3I Atlas demonstrates that these ingredients can be preserved in a stable state until the comet enters a warmer stellar environment. Its long journey through interstellar space implies that water and carbon-based volatiles can survive harsh cosmic conditions, including radiation and extreme cold, for extended periods. This durability increases the likelihood that the essential components for life are not only present, but also transportable between star systems, potentially playing a role in distributing prebiotic materials throughout the galaxy.
The implications extend to planetary formation as well. If interstellar comets like 3I Atlas are common, they may serve as reservoirs and delivery mechanisms for volatiles in young planetary systems. Water and CO2 trapped in these icy bodies could be incorporated into forming planets or moons, seeding them with essential compounds. This lends weight to the idea that the emergence of life, or at least the raw materials necessary for it, is not a rare occurrence confined to Earth-like environments, but a phenomenon that could be broadly distributed across many star systems. In addition, the chemical richness of 3I Atlas provides a comparative framework for understanding planetary system diversity. By observing a comet with a CO2-dominated composition alongside substantial water, astronomers can infer that different star systems may produce icy bodies with a wide variety of chemical balances, influenced by the temperature, density, and chemical abundances of the protoplanetary disk in which they formed. Such diversity suggests that the availability of water and organics in other systems may vary, but that the fundamental ingredients for life exist in multiple environments, enhancing the probability of life-friendly conditions elsewhere in the galaxy. 3I Atlas also reinforces the concept that interstellar objects are carriers of universal chemistry. Its journey demonstrates that key volatiles, including water and carbon dioxide, can traverse the galaxy intact, exposing the notion that these molecules are not confined to isolated stellar nurseries. Instead, they appear to be widespread, forming wherever conditions are favorable for icy bodies to condense and survive.
Each interstellar comet that passes through the solar system could therefore provide direct evidence of the distribution of life-essential compounds across the Milky Way, expanding our understanding of cosmic chemical abundance. In a broader astrobiological context, 3I Atlas lends empirical weight to the idea that life's building blocks are likely common in other planetary systems. While the presence of water alone does not guarantee life, it is a necessary ingredient for biochemistry as we understand it. The combination of water and carbon-based volatiles in an interstellar comet highlights the potential universality of prebiotic chemistry, suggesting that the raw materials for life are not constrained to our sun's neighborhood, but instead are a galactic phenomenon. In summary, 3I Atlas is not just a scientific curiosity. It is a symbol of cosmic possibility. Its water-rich activity, alongside a CO₂-dominated composition, provides compelling evidence that the ingredients for life are widespread, durable, and potentially transferable between star systems. By studying this extraordinary comet, astronomers gain insights into the abundance of water and organics in the galaxy, reinforcing the idea that life's essential components may be a common feature of planetary systems far beyond our own. The comet tells a story of universality, preservation, and interstellar chemistry, connecting the search for life on Earth to the broader context of the Milky Way. What makes 3I Atlas truly astonishing to the scientific community is the sheer unexpectedness of its behavior. No one anticipated encountering a comet with a CO₂-dominated coma that is simultaneously releasing water at such a prodigious rate at extreme distances from the Sun. Traditional models of cometary physics, based largely on solar system observations, predict that water sublimation should remain negligible beyond roughly 2 AU, while CO₂ and other highly volatile compounds may begin to sublimate at somewhat greater distances. Yet, 3I Atlas is defying these expectations on multiple fronts. It is venting water with a high efficiency, sustaining a coma far from the Sun, and doing so with an unusual chemical imbalance heavily favoring CO₂. This is not just a minor deviation, it is a dramatic departure from everything we thought we understood about cometary activity. The scientific surprise stems from how fundamentally 3I Atlas challenges long-standing assumptions about both thermal physics and interstellar chemistry. In models of solar system comets, water sublimation is closely tied to solar heating. The Sun provides the energy to convert frozen water into gas, creating the familiar bright coma and tails. At the same time, CO₂ and CO, which sublimate at lower temperatures, can generate early activity, but they rarely dominate the coma to this degree. 3I Atlas breaks this paradigm by exhibiting highly efficient water outflow at distances where water ice should essentially be inert, all while carbon dioxide dominates the outgassing composition. This combination was entirely unforeseen, leaving scientists scrambling to revise their understanding of comet activity under extreme and alien conditions. The discovery of 3I Atlas's activity is prompting a reevaluation of interstellar ice chemistry as well. Its unusual CO₂-to-water ratio suggests that the chemical environments in other star systems can produce cometary bodies with very different volatile distributions compared to solar system comets. Previously, models assumed that water-rich comets were a near-universal standard and that interstellar comets would roughly resemble solar system comets chemically, perhaps with minor variations in CO₂ or CO content. 3I Atlas is showing that these assumptions may be too narrow, and that interstellar comets can carry highly exotic chemical signatures, reflecting the colder, carbon-rich conditions of their formation environments. Even more surprising is the scale of its water release. Observations indicate that the comet is ejecting about 40 kilograms of water per second at a distance where water sublimation should be negligible. For comparison, many solar system comets only achieve comparable water production when they are much closer to the Sun. The fact that 3I Atlas can do this while still far out indicates the presence of processes not accounted for in standard models, whether trapped gases, chemical reactions within the ice, or pressure-driven venting from subsurface reservoirs. The efficiency and magnitude of its activity are rewriting the rules of what is considered physically possible for cometary outgassing. This scientific surprise also underscores the limitations of using solar system comets as proxies for interstellar comet behavior.
Oumuamua, for example, was a mysterious interstellar object with no detectable coma or gassing. It appeared entirely inert, and its elongated shape and mysterious trajectory sparked intense debate about its nature, even some questioning whether it was a natural object at all. Whatever its origin, Oumuamua lacked the volatile-driven activity that characterizes comets, providing little insight into the chemistry of interstellar ices. The second interstellar object, Borisov, discovered in 2019, resembled a typical solar system comet in many ways. It exhibited a clear coma and tail, largely dominated by water and with more modest quantities of carbon-based volatiles like CO. While Borisov was chemically alien, in the sense that it came from another star system, its composition and activity closely mirrored what we see in familiar comets, making it a reassuring, though still valuable example of interstellar comet behavior. Its activity followed conventional expectations. Water sublimation became significant as it approached the Sun, and CO and other volatiles played secondary roles. 3I Atlas, however, is breaking all these precedents and behaving in a completely new way. Unlike Oumuamua, it is actively outgassing, and unlike Borisov, it is doing so with a highly unusual chemical signature dominated by carbon dioxide, all while releasing water efficiently at distances far from the Sun where conventional sublimation should be negligible. Its large fraction of active surface, early onset of water release, and CO₂-to-water ratio of roughly 8:1 place it in a category entirely its own. No prior interstellar visitor has combined these traits, making 3I Atlas a fundamentally new type of object, one that challenges our assumptions about what interstellar comets can look like and how they behave.
This comparison highlights the diversity of interstellar objects. While Oumuamua was dry and enigmatic, and Borisov was familiar and predictable, 3I Atlas is hyperactive, chemically exotic, and physically distinctive. It demonstrates that interstellar comets are not a monolithic class. They can range from inert, rocky bodies to water-rich but otherwise conventional comets, to objects like 3I Atlas, which are both chemically alien and dynamically extreme. This diversity expands our understanding of what kinds of bodies other star systems can produce and what we might expect from future interstellar visitors. The contrast also emphasizes the scientific value of each interstellar encounter. Oumuamua challenged ideas about the shape, trajectory, and non-gravitational forces acting on small interstellar objects. Borisov provided a baseline for understanding cometary chemistry beyond the solar system. 3I Atlas, by exhibiting CO₂-dominated activity, early water release, and widespread venting, now challenges our models of cometary activity and interstellar ice chemistry, offering insights into planetary formation environments that are fundamentally different from our own. It is, in essence, the most instructive interstellar visitor yet, providing clues about both the chemistry and dynamics of alien comets. By observing these three interstellar objects sequentially, astronomers are beginning to see a spectrum of interstellar comet types. Some may be inert like Oumuamua, some may resemble solar system comets like Borisov, and some, like 3I Atlas, may be chemically and physically alien, defying expectations at multiple levels. This spectrum underscores the need to rethink models of comet formation in other star systems, taking into account the potential for extremely cold, carbon-rich environments and highly variable volatile distributions. In short, 3I Atlas is not just another interstellar visitor. Unlike its predecessors, it combines chemical alienness, hyperactive water release at extreme distances, and widespread surface activity in a way that is entirely unprecedented. Its behavior demonstrates that interstellar comets can surprise us in ways that solar system analogs never could, providing a vivid reminder that the galaxy is full of possibilities beyond our current understanding, and that each new visitor can teach us something fundamentally new about the cosmos. One of the most striking features of 3I Atlas is the sheer level of its activity, which is astonishing given its distance from the Sun. Typically, comets that are far beyond 3 astronomical units are faint and inactive, with water ice frozen solid and only the most volatile compounds like CO or CO2 able to sublimate at all. Yet 3I Atlas displays a brightness and gas output comparable to fully active comets located much closer to the Sun in the inner solar system. Its coma is expansive, dense, and luminous, signaling a vigorous release of gas and dust that would be entirely unexpected in such a cold environment. This makes 3I Atlas appear as though it has temporarily bypassed the usual thermal constraints that govern cometary activity. The brightness is directly linked to its gas production, primarily CO2 and water. Observations indicate that it is ejecting enormous quantities of material into space, creating a coma visible across multiple wavelengths. The water outflow alone is measured at around 40 kilograms per second, while CO2 dominates the coma with an even greater contribution. The combination of these volatiles drives a level of activity that rivals and in some ways surpasses solar system comets that have been heated to much higher temperatures closer to the Sun. This challenges our understanding of how energy, volatile composition, and surface area interact to produce visible cometary activity. The high level of activity also underscores the large fraction of the nucleus that is actively venting. Whereas most solar system comets have only a few % of their surface area participating in outgassing, 3I Atlas appears to be venting gas and ice from roughly a fifth of its surface. This widespread activity contributes to both the density and brightness of the coma, making it one of the most luminous comets observed at such a distance. It is this combination of early activation and extensive surface outgassing that gives 3I Atlas a presence normally associated with comets heated intensely by the Sun in the inner solar system. What makes this activity even more remarkable is the context in which it occurs. At over 3 times the Earth's sun distance, temperatures are extremely low, and sunlight is relatively weak. Under ordinary circumstances, water ice should be frozen solid, and even highly volatile compounds should only produce limited outgassing. Yet 3I Atlas defies these expectations, demonstrating a level of activity that mirrors that of inner solar system comets, indicating that some alternative mechanism such as CO2-driven venting, subsurface pressure, or chemical reactions within the ice is powering its energetic display. The visible impact of this activity is dramatic. Telescopes observing 3I Atlas report a large diffuse coma, indicative of sustained and vigorous outgassing. The brightness is not a brief flare or localized jet, but a global phenomenon affecting much of the common surface. The dust particles lifted by the escaping gases contribute to the reflective glow, making the comet appear more like a sun-warmed inner solar system body than a distant cold object. Its luminosity, combined with the extensive gaseous output, ensures that it can be studied in detail across multiple wavelengths, providing scientists with a rich dataset to understand its unprecedented behavior. This high activity also provides clues about its internal structure and thermal properties. To sustain such gas and dust release far from the Sun, 3I Atlas must contain reservoirs of volatiles that are easily mobilized and relatively close to the surface. Subsurface pockets of CO2 and other gases may be driving eruptions that, in turn, allow water ice to escape, amplifying the overall activity. The scale of this venting suggests that the nucleus of the comet is unusually porous or fractured, facilitating the movement of gases to the surface and sustaining a level of activity far above what is expected at this distance. In essence, the level of activity in 3I Atlas is both physically extreme and chemically revealing. Its coma is as bright and dense as that of inner solar system comets, yet it is being fueled in a frigid environment where conventional physics predicts near dormancy. This combination of brightness, high gas output, and extensive surface activity makes 3I Atlas a unique laboratory for studying the interplay of chemistry, physics, and interstellar comet evolution, offering insights into how icy bodies from other star systems can behave in ways entirely different from those formed in our solar system. By exhibiting activity levels normally reserved for warm, near-Sun comets, 3I Atlas demonstrates that distance from a star is not the sole determinant of cometary vigor, and that its alien composition and internal structure are key factors enabling this extraordinary behavior. This realization forces astronomers to rethink the parameters that control comet activity and to consider a broader spectrum of possibilities for interstellar visitors, where brightness, gas output, and volatile distribution can defy conventional expectations. The remarkable activity of 3I Atlas naturally leads to speculation about its internal structure and composition, which may hold the key to understanding why it is behaving so unusually far from the Sun. One compelling idea is that its nucleus contains layers of volatile materials that have remained completely insulated for millions, perhaps billions of years. These layers, rich in carbon dioxide, water ice, and potentially other exotic compounds, could have been trapped deep within the comet during its formation in a distant cold protoplanetary disk around another star. For the vast majority of its interstellar journey, these volatiles would have remained dormant, shielded from radiation and thermal effects, effectively frozen in time as the comet traversed the void between stars. As 3I Atlas approached the solar system, even the relatively weak sunlight it encountered may have been sufficient to begin warming the outermost layers, creating stress and fractures in the crust. These fractures could serve as conduits for the trapped volatiles to escape, allowing previously hidden CO2 and water to vent suddenly and efficiently. In essence, what astronomers are observing is not simply the sublimation of surface ice, but the awakening of deep, pristine layers of materials that have never been exposed to stellar heat or cosmic weathering. This process could explain both the magnitude of the activity and the unusual chemical balance of the outgas material, particularly the dominance of CO2.
The interior of 3I Atlas may also be stratified in a way that preserves volatile-rich layers beneath more inert crust, similar to a multi-layered cake of frozen gases and dust. Such stratification could allow CO2, which sublimates at lower temperatures, to escape first, generating enough pressure to fracture overlying layers and expose deeper water ice. Once exposed, the water can sublimate despite the cold ambient temperatures, creating the large-scale coma that has been observed. This layered structure might also explain why roughly a fifth of the comet's surface appears actively venting, a far greater fraction than typical solar system comets at comparable distances. Another intriguing possibility is that the comet's interior may contain volatile compounds or chemical clathrates that release gas in response to minimal heating or internal reactions. These compounds can store gases like CO2, CO, and methane within icy matrices, releasing them when structural changes or thermal expansion occurs. If 3I Atlas contains such materials, its current activity could be the first visible manifestation of chemical processes that have been ongoing quietly beneath the surface for eons. These processes may also contribute to the unexpected efficiency of water release, even at distances where sunlight is too weak to directly sublimate water ice. This perspective also aligns with the comet's interstellar heritage. Unlike solar system comets, which experience repeated perihelion passages and gradual volatile depletion, 3I Atlas has likely spent most of its existence in the deep freeze of interstellar space. Its volatiles, particularly the highly reactive CO2, may therefore be relatively unprocessed and abundant, making its internal composition both pristine and extraordinarily reactive once exposed to solar radiation. Observing the comet as it vents these previously untouched layers provides a rare opportunity to study primordial interstellar materials directly, offering insights into the chemical makeup of a star system far beyond our own. Speculating gently, one can imagine 3I Atlas as a time capsule from a distant planetary system, with its interior preserving a record of the conditions and materials from its birthplace. The sudden awakening of its volatiles, triggered by the gentle warmth of our sun, may represent the first time these materials have been exposed in millions of years, possibly since the comet formed. Each plume of CO2 and water vapor carries with it a fragment of that ancient alien environment, revealing not only the chemistry of the comet, but also the dynamics and structure of its interior.
In summary, the interior of 3I Atlas is likely a complex, layered repository of volatiles, long insulated from radiation and thermal energy, now venting dramatically as it experiences sunlight for the first time in its long interstellar journey. Its sudden and efficient release of water and CO2 offer a unique window into the inner workings of an interstellar comet, showing how ancient, pristine materials can drive activity far from a star, defying conventional expectations. By observing the interior indirectly through its outgassing, astronomers gain a rare glimpse into both the composition and structure of alien cometary nuclei, deepening our understanding of interstellar chemistry, planetary system formation, and the remarkable diversity of icy bodies across the galaxy. When we step back and consider all the remarkable features of 3I Atlas, its uniqueness becomes unmistakably clear. No comet in the solar system or any interstellar visitor previously observed has ever exhibited the combination of traits that make 3I Atlas so extraordinary. Its early onset of water release, occurring at distances where sunlight is far too weak to normally drive sublimation, sets it apart immediately. In almost every comet studied within the solar system, water ice remains dormant until the object approaches closer to the sun, typically inside 2AU. 3I Atlas defies this rule entirely, demonstrating vigorous activity in the cold outer regions of the solar system. Equally striking is the chemical composition of the comet. Its coma is dominated by carbon dioxide with a CO2-to-water ratio of roughly 8:1, a level of CO2 dominance never observed in solar system comets. Even interstellar comet Borisov, which resembled typical solar system comets in many ways, had a water-dominated composition. The unusual balance in 3I Atlas points to a formation environment that was far colder and richer in carbon than what we see in our own protoplanetary disk, highlighting its alien origins and giving astronomers a rare glimpse into the chemistry of a distant star system. In addition to timing and chemistry, the scale and intensity of its activity further reinforce its uniqueness. Approximately a fifth of its surface is actively venting gas and dust, far exceeding the few percent activity typical of most solar system comets at comparable distances. Its coma is bright and expansive, its gas output is prodigious, and its venting of water is highly efficient, conditions normally reserved for comets heated by intense sunlight in the inner solar system. Yet, 3I Atlas achieves all this while still in a frigid environment where traditional thermal models would predict near dormancy. This combination of early activity, high CO2 dominance, and extreme venting has never been seen before in any cometary body, whether interstellar or native to our solar system. Furthermore, the comet's interstellar origin adds an additional layer of significance. Unlike Oumuamua, which was dry, or Borisov, which resembled familiar comets, 3I Atlas behaves in a completely unprecedented way, combining chemical alienness with hyperactive venting far from any star. It serves as a living laboratory for understanding both the dynamics and the chemistry of icy bodies formed in alien planetary systems. Its composition, structure, and activity collectively provide insights that cannot be gained from solar system comets alone, giving astronomers a unique opportunity to study interstellar processes in real time.
In essence, 3I Atlas is a comet unlike any other. Its early, vigorous water release, CO2-dominated composition, and extraordinary level of activity at extreme distances from the Sun form a combination that is truly singular in the history of cometary observation. It challenges existing models of cometary physics, forces a re-evaluation of how interstellar comets might behave, and opens a window into the diversity of icy bodies across the galaxy. There is simply nothing else like it, and its study is poised to reshape our understanding of cometary activity, interstellar chemistry, and the potential for icy bodies to carry the ingredients for life across vast cosmic distances. Finally, as we step back and take in the full story of 3I Atlas, it is impossible not to feel a sense of cosmic wonder. This is not just another icy rock drifting through space, it is an interstellar traveler, a messenger from a distant star system
carrying within it the chemistry, history, and conditions of a place light years away. Its behavior, early water release, CO2 dominance, extreme activity, is a vivid demonstration that the universe is far more diverse and inventive than our solar system alone might suggest. 3I Atlas shows us that the rules we take for granted about cometary behavior are not universal, and that alien worlds can surprise us in ways both profound and beautiful. Its journey across the galaxy, preserving water and carbon dioxide ice over unimaginable distances, is a testament to the resilience and ubiquity of the fundamental ingredients of life. Even in the frigid emptiness of interstellar space, water survives, waiting for the first hint of stellar warmth to emerge once again. The sight of 3I Atlas venting water and CO2 in a region far colder than where most comets become active is a reminder that the universe is full of hidden reservoirs of chemistry, lying in wait, ready to interact with starlight and reveal their secrets. What makes 3I Atlas truly awe-inspiring is its dual role as both an alien object and a familiar one. While it comes from a star system beyond our own, it behaves in ways that connect with our understanding of cometary physics: gases escaping, dust being carried along, and a glowing coma forming in the dark. Yet it transcends those familiar patterns, showing that even across vast interstellar distances, the processes that produce water and drive cometary activity can manifest in astonishing ways. In observing it, astronomers are not only studying a comet, they're witnessing a story written across light years, one that links the distant past of another planetary system to the present of our own. Ultimately, 3I Atlas is more than a comet. It is a traveler, a messenger, and a natural laboratory all at once. It reminds us that water, and the potential for the chemistry of life, is not confined to the solar system, but exists throughout the galaxy, quietly enduring the journey between stars. As we watch it blaze a brief path through our celestial neighborhood, we are reminded of the vastness of the cosmos, the universality of chemistry, and the incredible stories that even small, icy objects can tell. In its brilliant coma and unusual venting, 3I Atlas tells a story of connection, resilience, and cosmic surprise. Across light years, from a distant star system to our own, it proves that water still finds a way to appear, that alien worlds can harbor familiar yet extraordinary chemistry, and that the universe is always capable of exceeding our expectations. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.